The old Powerball problem, eh? Going to draw a little coordinate system here. I'll call that the plus y direction. We got a little metal ball dropping with some velocity I'll call v. And the thing is, it's a constant speed in the downward direction there. So what we've got is a situation where the object is continually losing gravitational potential energy, U sub g, but it's not picking up any kinetic energy. It's losing mechanical energy, in other words. That must be being converted to thermal energy. So I'm interested in the power, which I can look at as the rate of change of the gravitational potential energy. Just rate of change of anything is the derivative of that something with respect to time. And indeed, we've got a case where the rate of change of something is, in general, how fast it's increasing. And we want to know how fast it's decreasing, so I'm going to take the negative of that because they want to know how fast the energy is decreasing. So it's the negative of how fast it's changing, in other words, the negative of how fast it's increasing, and that's what I got right here. Now, that's just going to be the negative of the derivative with respect to time of the gravitational potential energy, which is just mgy. If I use this, for instance, as a reference level. It doesn't actually matter what I use as a reference level, as long as I recognize that there is one established, because I'm just finding out how fast it's changing. I don't seem to care about what the value is. So we can write the power as mg is a constant, so I'll factor that out. That'll just be minus mg times dy by dt. So that's how fast the height is increasing, but that's just the negative of what I've defined to be v. I call it v downward positive, so this is negative v minus mg times just v with a minus sign in front of it, or just mgv. So the power turns out to be a pretty simple expression. Let's go ahead and evaluate that. That's P is equal to, let's see, the mass was given as 0.005. Kilograms. G, they give us a fairly accurate value. I think it was 9.8050 newtons per kilogram. I want to check on that. Yeah, 9.8050. And then we need V 0.0527. meters per second. So I want to check out the units for a second. The kilograms cancel. So I've got a newton meter, that's a joule per second. Newton meter per second, it's a joule per second, which is a watt. So we're going to have units of watts here. And I plug those values into my calculator, and I get 0.00258 watts. Alright, so that would be the answer, except we're given information on the uncertainty, so we got to do some error analysis. So see if I got enough room here to write use Gauss CP to evaluate P is equal to mgv with m is 0.00500 plus or minus. Now this bit means take the last two digits and consider them the uncertainty, and the last two digits would be, this was 3 zeros in front of it, so I'll go 0.123 and then the 50 kilograms. And what else we got? G, 9.8050, and then these two would be these two, so 2 zeros in front of that, plus or minus 0.0050. That'd be newtons per kilogram. And then V, given as 0.0527, plus or minus, and then this would be these two digits right here are uncertain, so it's 2 zeros, 0.0020. And the units are meters per second. So I got to plug all that stuff into GalCP. So let's go ahead and start up GalCP. I'll just fire up a browser, type in CB Physics. Pick the first item in the list. Go to first semester downloads, math resources, GalCP. Open that up. Double click. Open. And there we go. Starts up. They want my name first. So type your name in. I'll hit return. Come back over here to the function. I'm calling that P. I'm going to double click right here. Capital P for power, return. Capital P for power, return. Double click on this first tab. We were gunning for, let's see, capital P is equal to MGV. So I'll go change that to an M. Return, M return, and M is 0.5 plus or minus 0.5, 0.005, 0.0005. Hit return. The next variable is G. Type in G return. Oh, I meant to type in G return right there. Now I'm up to type in the 9.805. Return plus or minus 0.005. Okay, double click on the next variable. I'm going to call that V, lowercase v for the speed. Return, V return, and then 0.0527. Return and 0.002 return. And go back to my front sheet there. Gotta fix that up. Supposed to type in MGV. Oh boy, that's the default. It's 3 variables. I've got MG and V, so that's already taken care of. And this formula already reads M times G times V. So all I got to do is hit F9. So F9, just clicked on it, things changed. Let's see what we got. 0.02587. Remember, with my calculator I got 0.002587. I should say with the calculator I got 0.00258, which is what I've got up here. So excellent. We'll stick with the 0.00258. I do want to do this a couple of times. .odd 27. So I'll go F9. .odd 27 again. point triple odd 28, point triple odd 26, 29. So we got 6, 7, 8, and 9 so far. 27, 28, 27 again. Seem to be getting 27 most times, so I'll call it point triple odd 27. So go back over here to where I was solving the problem, and using Gauss P, we get, go ahead and write that down here. So with Gauss P, I obtain P is equal to 0.00258 plus or minus 0.00027. So it's out here in these last two digits where the uncertainty lies, and that's watts. So this will be my answer for the problem, obtained with the aid of